Can you hear me?
Hey, yes, can you hear me?
Hello.
How you doing, David?
Hey,
Hello.
Ian. Hey, everybody. Hey, folks, how are we doing tonight?
Good overall.
Good overall is good, I'd say. All right, give me a moment, folks. Okay. All right, I've got some cool stuff for all of you. Let me just let Schnorr in. Okay. All right. Thank you, James, for remembering to change your name on Zoom. I'm gonna change mine right now to include my pronouns. Very good, very good. I'm gonna ask again as a reminder that you all change your names on Zoom to include your pronouns, excuse me. And we're going to get started. How many of you had a chance to watch the stuff from earlier, the earlier classes lecture?
I watched most of it. We're like halfway through it.
Okay, yeah, I mean,
Well.
I wouldn't expect everybody to watch the whole thing, especially the end of it, because that's where I was addressing people's questions. So
Okay.
if you didn't answer that, I mean, if you didn't watch that part, that's fine. So once I just sort of say goodbye at whatever point in the video that is, you can log off then. You don't have to watch the whole thing. All right, so just to quickly summarize, could somebody tell us what they learned from watching that earlier video?
One thing I saw from that video was learning about latitude and longitude.
Okay, and could you share anything specific about them that you learned? Do you remember the difference?
Like between the hemispheres, yeah, there's that, and then also the equator and the prime meridian.
What else did anybody else pick up on in the video?
Looking up is like
How to judge distance, I mean size, and the degrees on how to use your hand to on degrees, like 1 degree.
Estimating angular size. It's good stuff. What else? I saw Andrea.
Oh, hi. So I was just saying, like, when you look up, it's like 90 degrees too. And I found it interesting to use your fists, like, to measure.
Yeah.
It was very interesting as well.
Yeah, who knew that you'd have such like a useful mechanism for figuring that out? That is like so perfect, almost so perfectly 10 degrees. I love it when it's like a nice round number, you know? Okay. So we were talking about that. We also introduced an important concept, which is the local sky and the celestial sphere. And what we're going to do right now is spend a little bit of time talking about those two. And I have some simulations that I'm going to share tonight to hopefully help make sense of that for all of us. Okay, so let me just pull up my slides very quickly. Where did this go? All right. Sorry, folks. Okay.
Professor, I have a question. Oh,
sure, don't worry.
Because I remember when I was watching the lecture, did we have homework? Like we had to complete the first set of problems?
This coming Sunday.
Okay, this coming
Sunday.
Okay.
And also the first lab. You'll find that
Sunday.
both are due this Sunday. If you don't complete, if you need like an extra day or so to do the lab, that should be fine. But yeah, that's this coming Sunday. right? And that homework is, the first homework is primarily on, you know, like converting numbers, scientific notation, doing a little bit of math, so on and so forth. So I'll dedicate the last 30 minutes of class time tonight to taking any questions that anybody has on the homeworks. I'm gonna share a screen here. Again, this is gonna be, I'm picking up where I left off. So if you didn't get to watch the earlier classes lecture, which I posted to Blackboard, you're just gonna have to do your best to follow along. I introduced two concepts. One of them is the local sky, and the other is the celestial sphere. And that conversation was preceded by talking about Earth's coordinate system, which includes a system of latitude and longitude, right? So we have a way of basically measuring how north or south of the equator a position is, and then also how far around the Earth is it. Using those lines of longitude, we can measure east or west of the prime meridian. Now, this screen that I'm sharing with you, it doesn't allow me to turn the celestial sphere, but it sort of looks like we're looking at this like not glowing, but like this orb of stars, all right? And this is essentially what our celestial sphere is, except the Earth is at the very center of this sphere. Okay, so I want to show everyone how we map the celestial sphere. Like, how do we map locations in the sky, you know, when the Earth rotates, and, you know, the angle of the Earth sometimes allows us to see certain parts of the sky, and sometimes it doesn't allow us to see certain parts of the sky. You know, how do we decide where something is? What are its coordinates in space when we don't have a solid ground to measure on? So you can see here, there's this yellow line that sort of wraps around. Right? This yellow line is the equivalent of the equator, right? This is like latitude on the sky, right? But then we can go above or below this celestial equator, right? We can go above it this way or below it that way. And basically, using this ability to rotate around with this other angle, which goes up and down, right? We can pinpoint any spot on this sphere. We can do anything in the southern hemisphere. We could do anything in the northern hemisphere. You can see I'm sort of like looping around the back. Right? And so these two coordinates are declination. That's this angle right here. Now it's a little bit hard to see, but I'm going to try to get this right on the side there. And it might be a little bit faint, but do you guys see that there's this like very light line that arcs across the top?
Yeah.
Okay, thank you, Daniela. So that line is cutting through, where is it? The North Celestial Pole. Oh man, I wish this would like let me drag it around. Shift click. Oh my gosh, that's amazing. Folks, I figured it out. I cracked the case. Okay, so there's our North Celestial Pole, right? And in the earlier lecture, I talked about how if you're standing at a certain spot, right? If you're standing at the North Pole and you wanted to look up at the North Celestial Pole, you would have to tilt your head up 90 degrees. Because if you're standing on Earth's North Pole, the North Celestial Pole is going to be directly above your head because the pole continues into the sky. It's an imaginary line, right? And so if I move my little cursor there all the way up to the top, you can sort of see this angle, the declination is 90 degrees. And that's because if we drew a line from the center of the Earth, or the center of the celestial sphere, which is like right in here, and we touched it to the celestial equator, or this yellow line, or excuse me, the white line, and we sort of arced it all the way up, right? How large of an angle are we sweeping out as we go from the horizon all the way up to that north celestial pole? And that comes out to about 90 degrees, right? Now, from the celestial equator to get to the south celestial pole, we could go 90 degrees the other way in the sky. And this is our declination of negative 90 degrees. Right, so just like on Earth, the North Pole is at the latitude 90 degrees north, and the South Pole is at 90 degrees south. On the celestial sphere, the North Celestial Pole is at 90 degrees positive 90 degrees, excuse me, and the South Celestial Pole is at negative 90 degrees. The confusing bit, I think, for some people is that instead of going around, let's see if I could find where the origin is. Right there. Okay. So as we go this way, right, sort of, I guess from a top-down view, that would sort of look like we're going counterclockwise, or excuse me, clockwise around. All right, we can all kind of see that. I'm going clockwise around the circle. All right. Instead of going 360 degrees and measuring how many degrees we have gone before we get back to our starting point, we're defining this angle in terms of hours, right? So if you think about it, the celestial sphere from Earth's perspective, right, the sky rotates once every 24 hours. So instead of measuring this in terms of degrees, we measure it in terms of hours, a complete rotation being 24 hours. Right? And you can see here when I move this around, this little alpha on the bottom, it says 0.9 hours. And as I move it over, you can see how many hours around. Right? So if this spot over here was 0, then a quarter of the way around would be a quarter of 24 hours. What's 24 divided by 4?
6.
6. So when I move the cursor over here, it should say, there it is, 6 hours. Right? 6 hours is a quarter of the way around. 12 hours would be halfway around the celestial sphere. Right? You can see it says 12 hours, so on and so forth. Right? So that is sort of the explanation with maybe a little bit of visual for the celestial sphere and its coordinate system. I'm going to pull up another thing now. Right, and so earlier I talked about the local sky, right, which is basically unique to wherever you're standing, right? Every single one of you has your own local sky because you're at the center of it, right? So every spot on Earth has its own local sky, which slightly changes how much of the sky is visible to you. And I sort of want to put in front of you these two different perspectives, right? I'm going to show you the local sky and the celestial sphere view at the same time for a person standing on Earth. And what I'd like for you to do while I'm pulling this up is I want you to look up the coordinates of LaGuardia Community College. I want to know, what are the latitude and longitude of LaGuardia Community College? All right, anybody figure it out?
40.7 north and 73.9 west.
All right, so 40.7 north and 73.9.
That's averaging
degrees.
it out.
All right, that's perfect. All right, you can kind of see here on the bottom that point looks to be around where Queens would probably end up. All right, so we've got two things going on here. we have the celestial sphere view. Typically, when we look at the celestial sphere, we orient it so that the north celestial pole and the south celestial pole make a vertical line. And you can kind of see here that these two little spokes, right, in the sphere, it almost looks like if you twisted them, the whole sphere would twist. Right? This is your north and south celestial pole. So you can see how it's oriented, right? Earth's equator is somewhere in here. And you can see that this yellow ring that goes around, that is the projection of Earth's equator onto the celestial sphere. So this is called the celestial equator. It separates the northern part of the celestial sphere from the southern part. Now, your local sky is what this simulation calls the horizon diagram view. All right, so here's a person standing out at LaGuardia Community College, right? And this is their view of the sky, okay? Anything below the green disk is below their horizon, right? It's hidden from their view. So what I'm gonna do is I'm gonna add a random star. You can see the star added itself down here. Now, from the horizon diagram view, all right, what we see here are the celestial equator. That's this yellow ring that looks like it arcs across the sky, right? This person, from their perspective, can see the north celestial pole. It's up there. The south celestial pole is down here, out of view. It's below the person's horizon, right? And then we have this single yellow arc across the sky here. It looks like it sort of cuts across east. Right? That is the 0 hour of right ascension. Okay, remember that's like the longitudinal equivalent of the celestial sphere. All right. The other thing that I want to point out is this very transparent looking line, it's very thin white line. This is the person's meridian. You see how it goes from north on their horizon all the way arcing through the sky. It passes through their zenith, the point directly overhead, and it connects to south. Or you can see it pretty clearly from this top-down view that this line right here is the person's meridian. All right, now we're just gonna turn the simulation on and I want you to just make some observations. All right, so in the celestial sphere view, the sphere remains fixed, but the Earth is rotating. All right, you see that? The Earth rotates, but the celestial sphere remains fixed. The horizon diagram view is showing what a person on Earth sees over the course of the day, right? So from their perspective, this person doesn't know that they're on a rotating planet. From this person's perspective, the sky is moving around them. And that's why both of these perspectives are useful, right? Both have their benefits. And I'm just gonna add some random stars here. All right, and you'll notice like this star on the bottom part of the celestial sphere in the southern part of the sky goes below this person's horizon. You see that? I'm sort of trailing along with it with my mouse. All right, it's just about to rise. There it comes over the person's horizon, crosses their meridian, and sets in the west. Right, we talk about how the sun rises in the east and sets in the west. As it turns out, all celestial objects do that. Everything rises in the east and sets in the west because it's the Earth rotating, right? The Earth is facing different parts of the sky throughout the day, right? Or at least your position on Earth turns to face all the different parts of the sky. I'm gonna add some more stars, just get a little crazy with it. All right, I'm gonna add some star trails. Does anybody here know what a star trail is? Okay, that's fine. Take a look here. I'm going to add short star trails. Right, so you can kind of see like the path of the star. What do you notice about their paths? I'm going to switch this to a longer star trail.
One of the things that I noticed is that the stars closer to like the top have a shorter radius, circumference compared to the other ones at the larger edges.
Yeah, 100%. Right? The ones that are closer to the poles, whether the north celestial pole or the south celestial pole, they have smaller circumferences, right? Smaller radiuses. What else do you guys notice?
Some stars spin fast and some take more time.
So that's an interesting observation. When you say that some of them move fast, do you mean complete their rotations faster? Or do you mean something different?
No, because not the rotation is faster, but the celestial is shorter than the other one.
Okay. Yeah. So, I mean, some of them certainly have shorter distances to go.
Yeah.
Right. But like, if you look at how much this star here, the one that my mouse is on, if you look at how fast that one appears to be moving around, it doesn't look like it's that fast compared to like this one over here. Right? Doesn't that one seem to be moving much faster? Right, look at the arc that it's sweeping out. This is a very large arc. Right, the star down here is moving very, very fast. Compared to this one, looks like it's kind of moving slowly along its path. So there are two kinds of things that we've got going on here. Certain stars cover more of an arc across the sky, depending on how close they are to the pole. The stars that stay close to the pole don't really appear to arc very much in a given time period because their paths are not as long. Let's talk about in terms of rising and setting, right? You know, we notice if you look here, there are a bunch of stars that dip below the person's horizon, right? So I'm just going to face this towards like the Western perspective. And you can see that as some of these stars come around, they dip below the horizon and then they're out of sight. You see that? Are all of the stars doing that?
No, it doesn't seem like it.
Which ones are not? Where would I have to look to find a star that's not rising or setting?
Like toward the bottom, no?
All right, so if you look towards the bottom here, right, see these stars down here, they actually never come above this person's horizon, right? There are certain stars for us in Queens, New York, that will never come into our view of the night sky. Conversely, there are stars in our sky that never set. They never go below our horizon. They are up 24 hours a day, right? And so we've got kind of a whole range of things happening here. We have stars that rise and set. They fall in this region, right? You see how anything that dips below or is above the horizon, if you're sort of looking through this transparency, anything that's down here never comes above the horizon. Anything up here never dips below the horizon, right? So there's a whole region of the sky of stars that just rise and set all day. All right, then we have stars that never rise. These are the ones at the bottom. All right, that's the never rise region. And then we have stars that are always out. These stars are called circumpolar stars. Circumpolar stars. And so you can see it here on the person's local sky view, but you can also see it on the celestial sphere. All right, so that's number one. Now let's change our observer's location. All right, I'm gonna bring our person from Queens up into
China.
Well, that's not really up. I think that's more over, but I can do that. I can bring this person over to China.
I'm sorry, Professor. You said with the circumpolar, like, what did you say about that? You said two different ones, two different
So
terms.
the circumpolar stars are stars that never set.
Okay.
All right, a circumpolar star is a star that never sets.
And do the ones that like never, they're always like at rise, do they have a certain term?
The one, which when you say the ones that are always at a rise, do you mean the ones that are always that rise and set throughout the day?
No.
Or do you mean the ones in the red region?
Right, the ones in the red regions.
Those are the circumpolar stars.
Okay.
Those are the ones that never set because they're always above your horizon no matter how much the Earth rotates.
Okay.
All right, good question. Okay, so what else do we have here?
Professor?
Yes.
Hi, I have a quick question. So the ones in the South Pole region, the blue region, those would not be considered circumpolar
Not for
stars?
us.
Yeah, not for us. But what about for
Mhm. But what about for who?
Yeah, for people that are in the South Pole, like closer to there in that area somehow, right?
Well, let's say I'm going to take this. I'm going to take
Go
the
south.
marker and I'm going to move it down into the southern hemisphere. I'm going to put it in Australia, and I want you to watch as I do that how the local sky diagram, the one on the right, changes. Okay.
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 That's
What did you
interesting.
see happen?
Well, yeah, like it is like in our view, but it's not as high up as I thought it would be, perhaps.
Okay.
But I think it's also
Maybe
because of the location, yeah.
so. Maybe we go to like the
What's
southern
that?
tip, but maybe we go to the southern tip of South America.
So it's
How about that?
basically the
Closer.
opposite from us.
Yeah, switched up.
Yeah.
Right, exactly. So for somebody in the southern hemisphere, they can see the south celestial pole. So let's do this a little bit differently. Let's start at the North Pole. So this is somebody who stands on the North Pole. Okay.
Okay.
What do you notice about the stars in their sky?
It
They
seems
never go down.
yeah, they
Yeah,
never
Available.
they never go down, right? They never see. So their horizon is the celestial equator. Right? Their
Yeah.
horizon is the celestial equator. And so they only see stars in the north celestial hemisphere. And as the Earth rotates, or rather as the celestial sphere rotates, you never get stars coming up above the celestial equator, right? The stars are fixed on the sphere, right? So this person is only ever going to see stars making circles around their heads. That's all they're ever going to see. And at their zenith is the north celestial pole, right? Now, as we start to go further south, right? Once you leave the North Pole, right? As soon as you walk south, your horizon dips below the celestial equator, right? You can start to see stars that are below the celestial equator. So watch this. Right, this person is at 80 degrees north. They're not at the North Pole. They're pretty far north, right? But just by changing the angle a little bit, there are now stars that rise and set, right? Because they can start to see stars from the southern part of the sky. If we go further down, right, the northern, excuse me, the stars that never set, that region starts to shrink. If you're looking at the stars that never rise, that also starts to shrink. And watch what happens when we get to the latitude of 0 degrees. In other words, we're at the equator. Look at this person's sky. Right? They're standing on the equator, and for them, the North Celestial Pole and the South Celestial Pole are both on their horizon. This person doesn't have to look up at all for them to see the North Star. It is right on their horizon. Right? And for them, every star, they get to see every star in the celestial sphere, no matter over the course of a day, right? Let me rephrase that. Because if the sun's out, you obviously can't see the stars in the sky, but they are there. For somebody who's standing at the equator, they have an equal view of the northern hemisphere as they do the southern hemisphere. So as the Earth rotates around them, they can see all of the stars in the northern celestial sphere that start to rise and then set. And they can see all the stars in the southern celestial hemisphere that rise and set, right? So while somebody at the equator won't have circumpolar stars, they also get to see every star. Okay. And so that's, some good stuff. So I want to make a connection here. Let me just see if there's anything that I forgot to mention here. Okay, I think that's pretty good for now. I'm going to close this. Did somebody have a question? I heard the breath.
So basically any country close to the equator will be better for stargazing. It's like
not necessarily. So it depends on what you're looking for. It depends on, there really is no good or bad, right? You can see the stars from anywhere, right? You can see the stars from anywhere. There are perks to not being at the equator also, and I'm going to share one of those perks with you in a second. Let me just now share my PowerPoint. It's one of the only annoying things about doing this is having to switch back and forth between so many different apps. Okay, here we go. So in this picture, okay, there is that arrow. What is that arrow pointing towards? Right. I'm giving you 3 options here. Think about what we just saw in our simulation.
The zenith.
Hey, the zenith.
All right. Anybody else agree with zenith? Anybody else have another idea?
I think it's B.
Yeah, North
Celestial Pole. Okay, so we got zenith, we got North Celestial Pole. Anybody for celestial equator? Okay, so how did we define zenith from the earlier lecture? How was zenith defined?
Directly over your head, like when you look directly up, that is your zenith.
Correct, you have to look straight up. Does this camera look like it's pointing straight up from this person's perspective?
Nope.
No.
So
Not
this
at
is
all.
not their zenith, right? It looks like, right? It looks like if you're, what are these lines?
The star trails.
Those are star trails. Notice that the star trails all appear to be rotating around this point where my mouse is. Right? Isn't that what it looks like? All the
Yeah.
stars are rotating around that point. So that is one of the poles, right? Everything rotates around the poles. So this spot here has to be the north celestial pole. And if I go back to the other simulation, hold on a sec, let me quickly do that. Bum, 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 bum. That's not the one I want. That's not the one I want. This is the one that I want. Okay, if I go back to this simulation and I turn on all the stars again, which I just added some, I added some stars there. Right. You can see here we've got the Big Dipper rotating around, and the north celestial pole over here appears to be fixed, right? The pole doesn't move. It looks like everything rotates around the pole, and that's true of the southern hemisphere also, right? In the southern part of the sky, everything rotates around the south celestial pole. So now let's go back. Now let me go back. Okay, now that we've made that important point. Share my PowerPoint screen. There we go. Okay, so this point is the north celestial pole, right? And at the north celestial pole is a star, which we call the North Star, right? And the North Star, over the course of many thousands of years, actually changes, right? The North Star is like a title given to a star. Currently, the star that's at or very, very close to our north celestial pole is called Polaris. You may have heard of Polaris before. It's Polaris, Polaris.
I pronounce it Polaris.
Yeah, no, it's we call it Polaris, and because Polaris essentially sits at the north celestial pole, it appears that all of the other stars in the sky rotate around Polaris over the course of the night. Over the course of 24 hours, the stars complete a full rotation about the pole. So how is that useful? Well, if you can figure out what the altitude of Polaris is, right? So if you can find the North Star in your sky, this only works for somebody in the Northern Hemisphere. If you can find the North Star, you can figure out what latitude you're at. Because the altitude of Polaris, the altitude of the celestial pole, will equal your latitude. Think about that, okay? Where on Earth are you standing if you have to look 90 degrees up above your horizon to see the North Star? Where are you standing on Earth if you have to look up 90 degrees to see the North Star?
The northern hemisphere.
Can you be more specific?
The North Pole.
You'd have to be standing at the North Pole, right? You'd have to be standing at the North Pole at 90 degrees north, so that if you look up 90 degrees, you see the North Star, right? And I'm trying to emphasize that the latitude of the person is equal to the angle that they have to look up. If you're on the equator, remember what we saw in the simulation a moment ago. When you're on the equator, you can look on your horizon and see both the North Celestial Pole and the South Celestial Pole, right? It is on your horizon. It is 0 degrees above your horizon. In other words, if you are at the latitude of 0 degrees, the altitude of the North Star is also 0 degrees. Well, hold on a second. What did we say our latitude was? Or what's the latitude of LaGuardia Community College? Yeah, I saw Danielle was mouthing it. I know it was in the chat before. It's about 40.8 degrees north, right? So if we are at 40.8 degrees north, then what is the altitude of the North Star in our horizon? Or excuse me, in our local sky? What is the altitude of the North Star in our local sky? How high is it above the horizon? Again, our latitude is 40.8 degrees. So what is the altitude of the North Star?
It's the same thing?
It's the same thing. Yeah, exactly. Exactly. It's 40.8 degrees. Now, earlier in the first lecture of the day, there was a technique presented for estimating angular distances, right? That an outstretched arm with a closed fist, from your perspective, from bottom of your fist to the top, that's about 10 degrees across the sky, right? If your arm is level with the horizon, right? So this is 0 degrees, that's 10 degrees, that's 20 degrees up here, that's 30 degrees, that's 40 degrees. Now, if I go outside and I turn my body to face due north, and I do this little trick where I go 10, 20, 30, 40, and I look in that direction in the sky, I should be staring straight at the North Star. And if you do that, then you will be looking straight at the North Star. That's how it works. So this was really useful, especially for early explorers who traveled across the Atlantic Ocean, who, you know, if you're traveling across the ocean, you don't have land to stand on. There are no markers for you to look at, right? There are no landmarks. So if you're in the middle of the ocean and it's nighttime and you're like, what the hell direction am I moving in? All you have to do is locate the North Star. Figure out how high it is above your horizon, and all of a sudden you know what latitude you're at, right? So if you know the latitude of your destination, you can keep yourself on track, all right? Okay. How about this? A little yes, no question for you. You can just type your answer in the chat here. A for yes, B for no. All right. Okay. Schnorr, why not?
Because it's north of the equator.
Yeah, if you're, because this location is north of the equator, right? So they can't see the South Celestial Pole. All right, if you're standing in the northern hemisphere on Earth and you're trying to see the South Celestial Pole, you won't see it until you reach the equator on your trip south. Right, like here's the Earth. Let me hold it like this. So here, this line is the equator. If you're standing here, then your local sky is this. Oh. Right, this is the person's local sky from where they're standing. And they have to walk all the way down to the equator. Now this is their observable sky, and all of a sudden the South Celestial Pole is in view for them. If this person works any farther south, right now the person's over here, this is their sky. And for them, the South Celestial Pole is fully in view. It actually never sets for them. So you can't see the South Celestial Pole from the Northern Hemisphere. Very, very good. Okay. So now we're going to talk about some of the motions of Earth. And there are a couple. Right. So the first two that we're going to talk about are rotation and revolution. Oftentimes people confuse the two. So you have to make sure that you know which one you're trying to talk about. Right? Rotation refers to Earth rotating on its own axis. Right? Earth rotating on its own axis like this. Okay? Revolving is the Earth going around the sun. So if this is the sun, the Earth going like this, that's revolution. This is rotation, right? The Earth does both of them. The Earth rotates on its axis while revolving around the sun. Okay? These motions are responsible for several phenomena that we experience on the day-to-day and the year-to-year. Right? This is, and we'll talk more specifically about each one. But this is why the Earth experiences day and night. Right? This is why the Earth experiences seasons. Right? Or part of why it experiences seasons. Right? So I would like for you to think about, actually, let me go to the next slide here. All right, so I'll just read this out loud for you. Every day, the sun looks like it's moving from east to west. Every night, the stars look like they're doing the same. The daily motion of the sun and stars is the most fundamental astronomical fact and the most basic illusion. In what sense is it an illusion?
I guess because it looks like, you know, the sun and stars are moving around us and the earth is at standing still. Is it that the illusion?
But what's the reality?
The earth is the one that's rotating.
Right. Right. So from the Earth observer's perspective, it looks like everything rotates around us. Right. We're the center of it all. We're so important. But the reality is, and we know this now, and we'll talk about the history of this school of thought. The reality is that it's the Earth that turns, and the stars that, for the most part, appear to stand still. Not totally true, but all right, it is the Earth that moves. Okay, so I want you to think about this, and I hope I don't hurt anybody's brain in the process. I want you to think about, how do you define a day? What is a day? And try not to look it up. Really just challenge yourself to define it on your own. We're all adults here. What is a day?
Rise and setting of the sun.
Okay. The rise and setting of the sun. So how long is a day?
24 hours.
Wait, yeah, I also forgot the rise and setting of the moon as well.
Okay. So Aman, what's this? What are you, let's tie that together for us.
Night and day.
Mohib, you can jump in a moment.
I don't know, a cycle of day and night.
Okay, a cycle of, so when you say day and night, you are, okay.
So having
All right,
the
that's
sun,
fine.
yeah.
So you're saying that a day is only while the sun is out.
Well, a day would consist of the sun being out and then the moon followed, and then the rising of a new day would be the next day.
So how long is that?
24 hours.
Okay. Mawahib, what were you going to say?
I'm going to say same thing. The day when the sun and then the night. This is a day.
Okay.
The day.
So if we go from the first daylight to the next daylight, right? So from dusk to dusk, or from dawn to dawn, one might say. Is that what you're thinking for a
Yes.
day? How many of you would agree with that? All right, looks like a couple of you are all about that. Damien's like, yes. James, what do you think?
I don't think that's right because throughout the year, time changes and the sun rises and the sun sets at different times throughout the year. So that doesn't make sense.
Also an interesting point. Okay. Also an interesting point. So there are two ways that you could define. Oh, Andre, do you want to say something?
Well, a day is one full rotation of the Earth. That's complete in 24 hours. So
Okay. So hold on a second. So now we're getting to something. Now we're getting to something else, right? Now you're saying that we're defining a day as one complete Earth rotation. So you're saying when the Earth rotates 360 degrees on its axis, that's a day. Is that what you're saying?
that's 24 hours. Yes.
Okay. That is not 24 hours.
Well, sorry.
No. But that's the misconception that I'm trying to draw out of everyone. That for the Earth to rotate one complete time on its axis is not 24 hours. That's
Okay.
not, that's when we talk about a day, when we talk about that, like amongst our communities, that's not how we define a day. We define a day as the length of time between the sun appearing in the same place in the sky. So, when does the sun cross your meridian? When is the next time the sun crosses your meridian? That's a solar day, right? And that's about 24 hours long. That is different than what you described, Andre, right? The other kind of day, because we have multiple definitions of what a day is. The other kind of day is called a sidereal day. It looks like the word sidereal, but it's sidereal. And that is the amount of time it takes the Earth to rotate once on its axis.
So, so hold up.
Yeah, I told you, I'm gonna be melting some brains tonight.
So it takes a solar day for the sun to pass our heads, or is that a sidereal day?
So
Within
a
the
solar
sidereal day?
So it's pronounced sidereal.
Sidereal, yeah.
Right, sidereal. Because we got to make it sound cool. Otherwise, sidereal. What the hell is sidereal?
It just sounds like a whack ass like cereal.
I agree. It's a terrible cereal name. So we got sidereal, all right, the cereal for astronomers. And then we have the solar day, all right? So the solar day is, all right, I want you to picture your meridian going overhead, cutting through your zenith from north to south, all right? And at noon, the sun crosses your zenith, all right? And then the sun passes into the other part of the sky, it sets. It's now nighttime. Later in the, a couple hours later, the sun rises again, and then it reaches the meridian, right? So from the sun touching your meridian to the next time the sun touches your meridian, that is a solar day, right? We're basing it on the sun's motion. That takes 24 hours, okay? That takes 24 hours. But the Earth only takes 23 hours, 56 minutes, and 4 seconds to rotate once on its axis. So why is there a discrepancy here, right? If the Earth completes a rotation, shouldn't the sun be at the same spot in the sky? The answer is no.
Because it waits until it has to pass the meridian, right? No.
Because so after the Earth rotates one full time on its axis, the sun almost makes it back to the meridian. It almost makes it all the way around.
Wait, isn't it because of the tilt of the Earth?
Nope.
On
We are
its
going to
axis?
talk about the Earth's tilt in a second. That's not
Okay.
why there's a difference. It's because the Earth revolves around the sun while it's rotating. Okay, so I'm going to exaggerate this a little bit, and then I'm going to pull it up on a slide. Okay.
All right.
This represents the sun. Here is the Earth. Okay. Actually, you know what? Yeah, I'll just
Yes,
do that.
Professor, you showed the video that it says one distance closer to the air on one side and the other was longer, the kilometers.
So that's also, I'll come back to that because that's something else, and we're going to talk about that too. All right. So if the Earth didn't revolve, right, then let's say that there's a person standing here. Can you guys see this clearly? All right. So there's a person standing on this spot. Hold on, let me stop the screen share so that anybody watching this video can see what I'm doing. Okay. This is the Earth, okay? And there's a person standing here. Actually, I'll make it where this little arrow looks like it's pointing, okay? And that person sees the sun in their sky. This represents the sun. And the Earth rotates once on its axis. Now, if the Earth doesn't move, then after one complete rotation, the sun is in the exact same spot, okay? But here's the problem, that as the Earth is rotating, it's also starting to revolve, right? So let me do it from this perspective, right? So the Earth rotates like this, right? So here's 24 hours, right? I'll do it one more time, 24 hours. Okay. Problem is that while that's happening, the Earth's also moving around the sun. So if the Earth moves around while it's doing a full rotation, the Earth just did a complete rotation, but this person who's standing on the edge of the Earth can't see the sun. The Earth has to rotate a little bit more because it moved ahead in its orbit. And so now I'm going to pull up the follow-up slide on PowerPoint. Let me make that full screen first. Try this again. Boom, boom, boom. This always takes me a second. Sorry. All right. So here's what we're looking at, okay? The passages of time, or the passage of time between positions 1 and 3 represents a solar day. Passage of time between 1 and 2 is a sidereal day. So this red arrow represents a person on Earth, okay? In going from position 1 to position 2, right, as the Earth revolves around the sun, the Earth rotates one complete time. But after this full rotation, the person's not looking at the sun, right? The sun is not crossing their meridian yet. So the Earth has to move a little bit more and rotate a little bit more than 360 degrees for the sun to come back into the same spot on the person's sky. And that's why there's a difference, right? So we have two ways of defining what a day is. How long it takes the Earth to complete a rotation, and how long it takes for the sun to get back to the same spot on your sky. We use the latter to define a day in our colloquial, in our day-to-day lives, right? 24 hours is a solar day. That brings us to revolution. Okay, so we talked about a day, right? The next part of what we observe, right, has to do with how the Earth moves around the sun. So throughout the year, you might recognize that certain constellations are visible and certain constellations are not visible. And that changes, as I mentioned, throughout the course of a year. So why does it change? Well, so we know that the Earth orbits around the sun, right? We know that the Earth completes these revolutions around the sun, which is sitting at the center of the solar system, and yada, yada, yada. But if the Earth is on one side of the sun, so here, this is marked February 21st, okay? On February 21st, the Earth is here. During the daytime, when you're on the side of the Earth that's facing the sun, you're also facing these constellations in the sky. You're facing Pisces, Aquarius, Capricornus, Sagittarius, so on and so forth. Problem is you can't see them because there's something that's preventing you from seeing those stars. The sun, right? The sun is out. So you can't see the stars in the sky, even though they're there, because the sun is just too bright, right? And we don't have a transparent atmosphere, at least not during the daytime. At nighttime, when you're on the side of the Earth that's not facing the sun, you can see Libra, Virgo, Leo, Cancer, Gemini, Taurus. But then fast forward 6 months. So we go from February 21st, halfway around our orbit of the sun. Now the Earth is here on August 21st. It is half its revolution around the sun. Now, during the daytime, the sun is obscuring your view of the same constellations that were visible on February 21st, right? On August 21st, if you are experiencing daytime, if the sun is up, so is Libra, Virgo, Leo, Cancer, Gemini, but you can't see them because the sun's out. But now you can start to see the other constellations: Aries, Pisces, Aquarius, Capricornus, Sagittarius. Okay. How many of you are big horoscope fans? Anybody? Okay.
That's interesting.
Yeah, I mean, I personally don't believe in it. I'm not telling anybody here what to believe, right? I think that there's certainly like I think anybody can find truth in reading a horoscope that says their sign on it. That being said, it's fun to read. How is your sign determined? Well, can anybody share what their sign is?
I'm a Scorpio.
Scorpio. Okay, so Daniela, so you were born sometime between October 21st and November 21st?
Mm-hmm.
Okay, so how do I figure that out? Because I'm not really good at remembering which sign is which birthdays. So your sign is determined by where the sun is on the celestial sphere at the time of your birth. Okay, so between October and 21st, November 21st, the Earth is somewhere in this little arc of its orbit. If I follow a line from this point through the sun is blocking the constellation of Scorpius. And that's why Daniela is a Scorpio.
So
Right?
that's why it's called a sun sign?
That's why it's
supposed to be your sun
correct.
sign.
Correct.
Okay. Wow.
Right. So somebody who was born in let's see, anybody have a birthday coming up in the next couple of days? Next week? This month? Anybody? Nobody?
April 1st.
April 1st. Okay. So April 1st, your sign is Pisces. Okay? Because on April 1st, somewhere around here, if you follow a line through the sun onto the zodiac, it covers the constellation of Pisces. All right, and that's pretty much how that's determined. So to quickly recap, right? Why do stars rise and set? Because of Earth's rotation. Right? Why do constellations we see depend on latitude and time of year? Well, it depends on latitude because where you are, what your latitude is, determines how much of the celestial sphere you can see. All right, remember what we said. If you're at the North Pole, you can only see the northern celestial hemisphere. If you're standing at the South Pole, you can only see the southern celestial hemisphere. And if you're standing at the equator, you can see half of both at any given point in time. Right? So where you are on Earth matters, but also the time of year matters, because the time of year is going to determine which constellations come out at night and which come out at daytime, regardless of your latitude. Right? So your latitude determines which constellations are possibly viewable to you. The time of year narrows that down, right, to a little subdivision. These are the ones that are visible during the summer months. Here are the ones that are visible during the fall months. Here are the ones that are visible during the winter months. Here are the ones that are visible during the spring months. And so why is it that we, speaking of seasons, why is it that we have seasons? I think Andre, you were mentioning something before, weren't you? About seasons?
No, only about the distance.
Okay, so hold on a second. I'm gonna go back to that slide that you're talking about.
Okay.
Is this one. So you're looking at the GIF on the bottom left. All right. What do we see here?
I mean, one side is less distant than the other. The revolution there.
Yeah, so the radius changes.
Yes.
Right. It's because Earth's orbit is not perfectly circular. Earth has an elliptical orbit. It's like a flattened circle. And so there are parts of the year where Earth is closer to the sun, parts of the year where Earth is farther from the sun. Right. I want you to go on a limb, folks, and I want you to take a guess. When is it summertime?
Right there.
How do you, when?
And the farther away. When it's close to the sun.
So it's you're saying it's summer when the Earth is at the position that's labeled here as 147.
Yes.
And it's winter when it says 152.
I guess.
Does that make sense, folks? It's summer when we're closer to the sun. It's winter when we're farther away from the sun.
I think so.
Think so? Mario, were you going to say something?
Yeah, I think so too.
Okay. Anybody disagree?
Kind of.
Why do you disagree, Nay?
I could be wrong, but doesn't it depend where you're located on Earth?
Elaborate on that. Why would that matter?
Oh, okay. I want to say something.
So, like, let's say if Earth is at the point where it's the closest to the sun, but you're not exactly facing it, then that doesn't consider it. It will be summer for you. It could still be winter for you, a little bit colder.
Okay.
I see another
but that's like how I was seeing it.
All right, folks, this is your conversation. Just chime in. Just chime in.
So if the sun is closer to the air, only gonna see less. It's gonna be winter. Sorry, I changed my point of view, because when it's close, the sun doesn't give too much heat. Why? When it's far away. So close to the sun, it will be winter, because only show the heat and certain points, and when it's farther, it's wider, so it's give you more heat day.
Okay,
Kinda.
I want to push back on that logic for 1 second, Andre, because I'm going to say if there's a fire pit, right? As you move farther away from the fire pit, are you feeling more heat or less heat?
Let's see, but I can still see the light.
You can still see the light, but you are feeling less heat.
Yes.
Right. That energy is less intense as you get farther away. I'm going to go ahead and say the same thing, right? That the energy is more intense from the sun when the Earth is closer to it. Taisuke, can you add to the conversation?
I just have a question. So
Sure.
it takes 365 days for Earth to go around the sun?
Yes, just about.
Yeah, right. Okay.
Yeah, it takes 365.25. 365 and a quarter days to go around the sun.
Right. Okay.
And that's why every 4 years we have a leap year. We
Right.
add a day. So as it turns out, I think actually Nay was saying it before, that when it's summer in the northern hemisphere, is it also summer in the southern hemisphere?
No,
No, it's not. So
it's the opposite.
so if it could be summer in one hemisphere and winter in the other hemisphere, regardless of how close the Earth is to the sun, right? So the proximity to the sun is not actually what determines the season, which is confusing for a lot of people, because they're saying, oh, if we're closer, it should be hotter. Let me fast forward through my slides now.
I think summer is summer everywhere. I compare to, I live here in my country, summer is summer, summer here, summer there. But there is too hot and different, it's different temperature. Winter there, winter here.
So Mawahib, what I'd like to know is, what is the latitude of the country that you're referring to?
My country is under the equator.
Ecuador.
Yeah.
Okay. Okay.
Yeah, it is.
So it's near 0 degrees. It's near 0 degrees latitude.
Yeah.
So the seasons there are actually kind of not as pronounced, right? Like you're still not.
We don't have spring, no spring.
Yeah,
Just, yeah.
Right. It's like it's really like the wet and the dry season, right?
Mm-hmm.
Right. It's not so much winter, spring, summer, fall. Is it wet or dry outside? So why do we experience the season, right? If it's not proximity to the sun, what is it? Well, Earth, we established that Earth rotates on its axis, okay? But the axis of its rotation is tilted. Okay, so let me go back here to this picture, right? The Earth makes a disk around the sun, okay? The Earth makes a disk around the sun. And you might be thinking to yourself, well, are the North and South poles pointing up and down with respect to this disk? You see how I'm just kind of drawing them perpendicular to the disk. All right. And this is incorrect, right? This is not what's happening. The reality is that the Earth's rotational axis is tilted. Okay. So I want you to just first watch the left side, okay? As the Earth goes around, let me actually give it this top view. You can see how the axis sort of like points directly to the left side of the screen. As I move through time here, that the tilt of that little axis still points to the left. Do you see that? All right, so Earth's axis is tilted. This axis does not go straight up and down. It's angled with respect to its orbit, the orbital plane around the sun. All right, and so, let's go to June. All right, in June, do you see this white spot over here? That is the point directly below the sun on Earth's surface. If you were standing at that point, the sun would pass through your zenith at noon. There's a red line in there also. right? And below that, there's this blue line. Can you guys see that? Okay, this blue line where my mouse is touching, that's the equator. In June, at this time of year, the sun is directly overhead in the northern hemisphere. So the northern hemisphere is getting direct sunlight. Watch this. If I change this person's latitude, I don't even remember how I do that. Oh, here. Right. So here's a person, I just moved them onto the point where the sun's directly overhead. And so for them, the sun's rays are coming straight down, very intense. You could probably think of a time where you were standing under such direct sunlight. But fast forward 6 months, right? Now, when we look at the sun, the northern hemisphere is tilted away, but the southern hemisphere is getting the most direct sunlight. Right? This causes it to be winter in the northern hemisphere, while it's summer in the southern hemisphere. All right. And so, let me put that back for a second. All right. So this is like the first day of winter, right? And now for that same person that was originally standing in the northern hemisphere, look at the angle of the sunlight. It's coming at a very low angle compared to when it was directly overhead. And for this reason, the sunlight is spread out over a larger swath of ground. And so it's not as intense, right? And you can sort of mimic that. You can demonstrate that if you have a flashlight or a cell phone, in my case, right? And you can take it and you can put it down directly overhead, or you can do it at an angle. And when you do it at an angle, the intensity of that sunlight on the ground becomes smaller. Do you guys see that? You can see it looks a lot brighter. All right. So the reason that we have seasons is because Earth's rotational axis is tilted. Now, I wonder if I change this. Okay. So watch this. So this is sort of the let me actually fast forward a little bit. Let me stop the animation. I'm going to move this to March 21st. Okay. On March 21st, where is the sun directly overhead? What latitude is this? It might also be helpful. Yeah, it's directly overhead the equator.
Equator.
What that means is that on this day, the northern hemisphere and the southern hemisphere both get an equal amount of light. This is called an equinox. Has anybody heard of the term equinox before?
Yes.
Does anybody know what it means? So if you break it up into equi and nox, equinox, equinox,
yep.
Equal night. On this day, every single person on Earth, no matter where you are, gets 12 hours of daylight and 12 hours of nighttime. 12 hours of light, 12 hours of darkness. All right. There are 2 equinoxes throughout the year. One of them is on the first day of spring, and the other is on the first day of fall. All right. They are the vernal equinox and the autumnal equinox. I will put that up in just a moment. And then we have the solstices. These are the first days of summer or winter. It depends on which hemisphere you're in. The date depends on which hemisphere you're in, right? So the winter solstice for the northern hemisphere is December 21st. That is also the summer solstice for the southern hemisphere, because the southern hemisphere has everything opposite the northern hemisphere. All right, so I want to now change perspectives for a second. So right now we're looking at the orbit view. Okay, this is the perspective that the sun is the thing that's stationary and the earth is orbiting around it. But now let's switch this up to the celestial sphere view. Okay, the green ring represents the celestial equator, right? That's the projection of the equator. This is dividing the northern celestial hemisphere from the southern celestial hemisphere. This yellow line is called the ecliptic. The ecliptic, I'll put that up on a slide in a second. The ecliptic is the path of the sun over the course of a year as it moves around the celestial sphere. Now, why does the sun appear to move around the celestial sphere? Well, it's because the earth is actually revolving around the sun, right? And the sun covers different constellations over the course of the year. The reason that the ecliptic and the celestial equator don't overlap is because Earth is tilted, right? If the Earth and its rotational axis were not tilted with respect to its orbital plane, then the sun would lie on the celestial equator. Problem is, the Earth's not oriented like this. The Earth's axis is tilted. So Earth's celestial equator goes around this way, but the sun travels around this way from the Earth perspective, right? Now, what you see here, and if you pay attention to the months on the bottom, let me start this over. So this is like right around March 21st, okay? On March 21st, the sun is directly overhead the equator. Do you guys see that? It is half above and half below the celestial equator. So both hemispheres on Earth receive the same amount of sunlight. But as we in the northern hemisphere start to get closer to June, we start to get closer to summertime, because the sun starts to become more and more overhead in the northern hemisphere. Right? After March 21st, because of Earth's tilt, the sun gets further and further into the northern part of the celestial sphere, such that on June 21st, June 22nd, the sun is at its highest part in the celestial sphere. It is most overhead in the northern hemisphere. This is the longest day of the year for somebody living where we live. Right? We have the most hours of daylight on this day. Then we fast forward 3 months from June 21st to September 21st. And on September 21st, we are at another equinox. We are now, yes.
Professor, so that's the longer distance or the shorter distance? Winter and summer?
When we experience summer,
yes,
in the northern hemisphere,
yes, that's the one.
The Earth is farther away from the sun.
Okay, that was right at the end.
Right, but the southern hemisphere has
it's
summer,
different. Yeah.
Right. So even so, we're in any case. Now we fast forward. And then from September all the way back to March, the sun is in the southern part of the celestial sphere. And so for 6 months, the southern hemisphere gets warmer weather than the northern hemisphere, right? And that's really it. The reason that we have seasons is just because Earth's rotational axis is tilted, right? If Earth's axis were not tilted with respect to its orbit, it would be the same climate all year long. We wouldn't have winter, spring, summer, fall. Right? And if there was a planet whose orbital tilt was so extreme, right, that instead of having no orbital tilt, it had a tilt of like 90 degrees. It's basically rotating on its side as it moves around the sun. It would have incredibly extreme seasons. It would have extreme summers and extreme winters. All right, let me go back to my slide. I'm just going to wrap up, and then we can say goodnight. Oh. All right, so we already established that. Let's get back to this. Okay, all right, so the reason that we have seasons is that Earth's rotational axis is tilted 23.5 degrees. 23.5 degrees. That number you might recognize if you've ever looked at a globe. If you look at a globe, all right, or a map, you'll notice that there are certain lines that are marked off. There are certain lines of latitude that are marked. One of them is the equator. Then there's 23.5 degrees north, which is the Tropic of Cancer. In the southern hemisphere, you have 23.5 degrees south. That's the Tropic of Capricorn. You also have the Arctic Circle at 66.5 or so degrees north, and the Antarctic Circle at 66.5 degrees south. Right. In this position, okay, in this position, let's say that the northern hemisphere is at the top. As the Earth rotates, if somebody is standing at the North Pole of Earth, as the Earth rotates once on its axis, will the sun ever rise for this person?
I think no. Would it still stay the same? Or
The sun, well, the sun will not rise for this person. I'm going to quickly draw for you their horizon. Right, so for a person who's standing at the North Pole, right up there, they can't see anything below this green line. Right, that from their perspective, that's the horizon, right? That's determined by the ground below their feet. As the Earth rotates, the sun will never come above this line. And so on this day, this is the first day of winter for the Northern Hemisphere, because the Northern Hemisphere is tilted away from the sun. The Southern Hemisphere is tilted towards the sun. Right. On this day, this person experiences 24 hours of darkness. The sun never rises. Remember that the sun is just a star, right? Just like all other stars. Right? Some stars never rise, some stars never set. Some stars rise and set, right? And so that depends on your latitude, right? For us in Queens, the sun always rises and sets, but it never just stays out, or it never just stays hidden. But if you're at the North Pole, on this day, the sun does not come out at all. It is 24 hours of darkness. And in the Southern Hemisphere, at the South Pole, for this, oh, what the hell just happened? For this person who has one really long leg, the sun never sets, or they have 24 hours of daylight. And I think that I've got it actually. So these are the dates, right? And just speaking to what Andre mentioned before, I wanted to note that the distance between Earth and Sun does not affect the seasons, right? How close or far the Earth is does not affect the seasons one bit. The only thing that affects it is whether or not your hemisphere is tilted towards or away from the sun. That's the only thing that determines what season it is at your location. Okay. So we've got the vernal equinox upon us on Sunday, right? So this coming Sunday is the first day of spring. On that day, you can time it if you'd like. You have 12 hours of daylight, 12 hours of darkness on that day. And that's going to be true for everybody on Earth. Let me wrap things up because I am approaching my limit here. We'll revisit this next Monday, the path of the sun. We'll talk about that next Monday. Right? And I kind of sort of addressed this thought question before. I said if Earth's axis were tilted 90 degrees instead of 23.5, right, the seasons would be exaggerated. Right? The seasons would be even more extreme. And this is the next picture I wanted to show you. So this is, although Alaska is not at the North Pole, Alaska is far enough north that the sun doesn't set for them on the summer solstice. And so this point right here in the middle, when the sun is at its lowest spot in the sky, this is a composite image of the sun at 1 hour apart. When it's at this lowest spot, that's midnight. The sun is up at midnight above the horizon because it does not set at this latitude at this time of year. All right. So this is some cool stuff, I think. All right. And with that, if anybody has any questions, now's the time to ask. Otherwise, you can head out. Just remember that you have a couple of things due this week. There's the first homework assignment on Blackboard. Hold on one second. Right, there's the first problem set. There is the first lab on lunar phases, and there's the week 2 discussion prompt. All right, so make sure that, now that hopefully everybody here has gotten the chance to post for week 1. If you haven't, make sure that you do. That you post your initial week 2 post earlier than later, because you want to give people time to respond to it. And you want to make sure that other people give you time to respond to them, right? If everybody just waits till Sunday, you're all going to be scrambling. Lunar phases means the phases of the moon, right? So full moon, new moon, first quarter moon, waxing crescent,
Waning moons.
Yeah, exactly.
Yeah, I get what you mean. I'm just making sure.
All right, no problem. So you have 3 things that are due this week, right? The week 2 discussion, the first lab, the first problem set for homework. All right. Just be mindful, because for whatever reason, I can't get my open math to put the due dates on Blackboard. All right. So for those assignments, you have to be cognizant of the syllabus. All right. I'll put a reminder up, but you need to make sure that you have that calendar, because I'm not going to change those due dates. All right. I promise you that I will not change them. Okay. So unless there are any other questions, you can head out. Enjoy the rest of your week. Enjoy the first day of spring coming up. And I will see you all on Monday.
I have 2 questions, Professor.
Yes.
For the first problem,